so that when I stand here, I can be somewhat visible. Yeah. Hi, Henry. No problem. Got it. Got it.
You told me.
Got it.
There was no one.
You have to accept.
What?
It's being broadcast.
Yes.
Okay. Okay.
Very good. So I'm very glad to announce our first in-person meeting of this seminar and announce the talk of Siddharth Sahi from Rutgers University on random and mean Lyapunov exponents for GNR.
Okay, thank you. And this is joined with Diego Armentato, Gautam Chinta, and Michael Shub. So let me explain what is the. Okay, so I explained the. Okay, so so G will be GLNR. K will be ONR. Okay, so if G is in G, I will write, this means the operator norm. Okay, maybe lambda G is log of the operator norm, and maybe, yeah, that's fine. Okay, so this is the setup, and now suppose, okay, maybe I write here. Okay, so suppose mu is a probability measure on G such that, so I'm going to impose some mild condition, and this condition is such that this function max of lambda G0, so log of the operator, this should be G, such that this belongs to, this is an L1 function with respect to them. Okay, so it's some mild technical condition on the probability measure. So in this situation, there is a theorem, so let's call this star. So there's a theorem of WIS. I don't know how to spell this name. Apparently, this kind of. So this is what my co-authors use, but sometimes there was a C or.
There should definitely be a wow between the S and the L.
Ocelladets. Ocelladets. Yeah, I'm probably saying it incorrectly. Ocelladets.
Dima could write it in Russian.
That's correct.
Dima could write it in Russian.
I could write it in Russian, yes, if I knew how. So there's a theorem of Ocelladets that says the following, that suppose mu satisfies star, then there exist n real numbers, and I will just order them. So R1 bigger than R2 bigger than Rn. such that for almost every new RID sequence, say G1, G2, etc. in G, and for any vector v not equal to 0 in Rn, the limit so I take the limit m goes to infinity of 1 over n times the log of the Euclid. Now this is a Euclidean norm. Okay, maybe I should write up here. Euclidean norm Gm G1 applied to V sub 2, the Euclidean norm. This exists and equals 1 of the Ri. Okay. So that's some very nice theorem. And yeah, so these numbers so we will say that the Ri, which will be dependent on mu, are the random Lyapunov exponents of mu. Okay. Do you have any questions? So for any probability measure, so this is like a random product with respect to the measure mu. So you take a random product, apply it to any non-zero vector, and you do a scaled limit.
One word.
Yeah.
For every mu, what sequence?
Yeah, thank you. So I choose the G1, G2, etc. independently with the distribution mu. So I just sample from the group according to this measure, probability measure mu, but independent. So IID is independent and identically distributed like mu.
One of the Ri's meaning the coordinates of the
Still just some universal numbers. So this is Osladet's theorem.
and for the Haar measure of that.
Haar measure is not a probability measure. It's not finite. This is for each probability measure, there's such a thing. Okay.
If we take probability measure on K and extend it by 0.
Okay, I will give an example in a moment, right? I will give an example which is going to be crucial. And guess so I give an example.
Dima, in this case, K doesn't change the size, so the limit it's a fixed sequence.
Sorry, Itan, what did you? K doesn't change the size. Yeah, K doesn't change the size. Yeah, K doesn't change the size. So all of the numbers are equal to 1 or maybe 0. Okay, anyway. Depends. No, just 1. Yeah. Okay, anyway, we'll see. We'll see in a moment. No, this number is constant, so 1 over m of that goes to 0.
Yeah, sure. Stupid question.
No, not stupid question, but I didn't think about it, but maybe that's the answer. Yeah. Okay. Very good. So, okay, so these are the random determinate exponents. Okay, but there is an interesting special case. So I do want to consider the special case when mu is concentrated on a single on a single matrix. So it's the other extreme, just the delta. If mu is concentrated on a single on a single matrix A, yes. So suppose. So now the exponents depend on the eigenvalues of A. So suppose, so let lambda I of A be the eigenvalues, lambda 1 lambda n A be the eigenvalues. Values of A, and let us put L. So they're not quite the eigenvalues of A. You will see in a moment what they are. What they are exactly, and then let's just put Li of A to be the log of the absolute value of the eigenvalues. Okay, because eigenvalues don't have to be real numbers, but take absolute value and then take log of that. Then, okay, so if V, so let's say Vi is an eigenvector with, sorry, let's say correspond with eigenvalue lambda I, then okay, the sequence is just A. That's not changing, right? So then, if I compute this limit, so what I have to compute is this limit m goes to infinity, 1 over m, log of norm of A to the m, Vi, right? And this is 1 over m times log of lambda I of A to the m times Vi. This is 1 over m times, okay, this is some scalar, so I pull it out. It's log of absolute value of lambda A times m plus the norm of V, because it's this times that, so just becomes plus, and this just approaches Li of A. As m goes to infinity, the norm of V actually just drops out of this picture, as long as it's different from 0. Oh, no, it should be log of the norm of V, but never mind. It doesn't scale. It gets killed. Is this clear?
I'm sorry, what's the question? So what is wrong with taking arbitrary G in general? So I mean, here you're saying that you take...
It's just separated on one point.
Okay, yes, but in general, if you take just an arbitrary mu, and you take an arbitrary matrix A, what's wrong with that?
What's wrong?
I mean, your computation shows that if you have a...
So, okay, maybe that the sequence A has probability 0. So the point is that it's for almost every sequence.
So the statement of the theorem, oh, I see.
Yeah, you cannot say about any particular sequence, but it's true for almost every sequence. depending on the measure. So it's just some subtle state theorem. Yeah, sorry, is this clear? Should maybe I write, let me just write it. Huh? It's clear to everybody, anybody in the audience, you know. It's all good, right? Okay. Okay, fine. So so this means so those are the Lyapunov exponents in this special case.
The only thing we don't give, and it's true, is that the matrix is not diagonalizable. Maybe we didn't get enough eigenvectors.
Oh, yeah. I mean, I don't. Yeah, no. I should say a little bit more, right? Okay, if so more generally, okay, I didn't explain that these are the so okay. So more generally, okay. Let's suppose you know, as before, that lambda 1a is bigger than or equal to lambda 2a is bigger than or equal to lambda na. Right, so then of course L1 Ln, and now let's suppose this, and now if B is of the form, if V okay, if V is equal to I don't know, U plus W, where U belongs to this, U is an eigenvector. This corresponds to lambda alpha, and W belongs to the higher eigenspaces, generalized eigenspaces. Well, higher, okay, in the sense that lower, okay, eigenspaces. So eigenspaces for J span belongs to the span bigger than lambda J, J bigger than I. So this is the dominant guy. Then again, this limit, then again, this limit is going to be equal to Li. Okay. Because the lower things would die.
Sorry, I still don't understand completely, but may I ask a question about just the statement of the theorems?
Yeah.
So the theorem says that for almost every sequence.
Yeah.
What does this mean here? So almost every means except one measure is 0 or what?
Yeah.
But what is the space? I mean,
Respectable sequences with the coded measure.
but is it correctly defined?
Yeah.
It's finite sequence.
No, infinite sequence.
Infinite sequence.
Yeah.
But
So what?
You say the product of coordinates.
so you don't need any kind of stabilization?
No.
No. Yeah, this is kind of
It's called the Bernoulli process.
Yeah. Right. Like in the strong law of large numbers. It's the same idea as the weak law versus the strong laws. It's a strong law statement. Yes, you will tell me if I say something wrong because you must. Okay. I'll say it again.
Oh, so much more than I.
Oh, but just very narrowly, but yeah, I have, because I did something here. This is why I know something here. But anyway, this is the, okay. So this is, so that's, okay. So this is again true. Okay. So now let me define. So I want to state my main theorem.
Sorry, there are n numbers. It's the same n as in GLM.
Yes. It's the same n as in the number of eigenvalues with repetition. Yeah. I mean, if the measure is just a point measure, then it's essentially eigenvalues. It's the LIs rather than the lambda i's. And in general, the point is that for any measure, this is true in the strong sense. Yes, it's okay. Anyway, so right. So what was I going to say? Okay. So all right. So now let me. So okay. So now I want to state my. So I want to state our theorem. I want to make a definition. Okay, so I'll just make the definition. Okay, so let us define. Let us define. So I will put R sub k to be the summation I goes from 1 to k of little r sub k. Okay, of mu.
R sub I.
Thank you, r sub I, but I want to take the max with 0. Okay, I mean, this depends on mu, of course. And then I will put similarly L sub k. So L sub k of A, okay, R sub k of mu. L sub k of A is the same thing. It's the max of the sum of the LIs. Okay, I should maybe write of mu. Okay, so I want to relate these exponents to those to the Lyapunov exponents, and so the theorem of ACSS.
So is there some concrete way how you order your exponents?
Right, in decreasing order. The indexing is in decreasing order, and also for the LIs. Otherwise, I would have to do something more. Right, so let's order them. They're real numbers, so I can order them. Yeah, so the theorem is that okay, no. I need to say, I need to impose some condition on the measure for this theorem to be true. So suppose mu satisfies suppose mu satisfies. Okay, suppose mu is a probability measure. Okay, maybe I write it. Okay, suppose mu is a left O and R invariant probability measure. On maybe I just say K invariant. I said K was O and R on G, this is G and R. So it's not true for arbitrary measures. It's kind of what I'm about to say, but suppose it's left invariant. So not a point measure. Okay. Suppose a left invariant measure and such that the same condition such that this max such that max of lambda G0, but also max lambda G inverse 0 are in L1 mu. So I will call this condition double star. Okay, so I need I need it to be true for it needs to be invariant by K, and both lambda G and lambda G inverse have to be in L1. Then the theorem is this, ACSS. So if mu satisfies double star, then this I can take LKG so I can take the individual for these guys and average it over the group. Mu. Yeah. Then this is this is bigger than some constant, or some, then there exists a constant C. Such that, well, I mean, C equals, it depends on M, okay, the constant depends on N, but not on mu or anything.
Sorry for a stupid question, but why such a mu exists at all? So I mean, is there some example of K invariant measure or G?
If you have any probability measure, let's say you could just have some measure with support away from, so if you have some compactly supported measure, you can always average it on the left by K and make it K invariant. That's not a problem.
Average, so the group is infinite, so I mean, is it still fine?
No, K is finite. K is compact.
So averaging means that you take your set, yes, and just shift it by all the elements.
So of some function is the integral of the K average of that function. The K, then your such a measure is K invariant. Is it?
Take K equals 1.
Who?
Suppose I take the K equals 1.
K. Little K equals 1.
No, the bottom.
No, K equals 1. It's the top.
So the top Lyapunov exponent is bigger than or equal to a constant times the top average eigenvalue. So the top.
So I get an upper bound for the.
The top Lyapunov exponent.
I take the top value and I average it over the group with respect to the measure.
The average top eigenvalue is bigger than
first Lyapunov exponent.
the average first Lyapunov.
No, first Lyapunov. The average involves the measure. The Lyapunov exponent of the measure is no more averaging.
Oh, of course. It's almost surely constant. I see. Wow.
Yeah. Yes. Yeah.
And C depends on N?
Huh?
C
depends on N, yeah. You can write it down explicitly. It involves some ignore something like Euclidean volumes of orthogonal groups or some stuff like that.
So you like actually have like some kind of extreme example where C is.
Well, I mean, like, okay, I should say there exists explicit constant. So I'm not sort of trying to fight the constants here. But the point is the constant doesn't depend on the measure.
But can you say what is the external measure for which the equality holds?
I know I cannot. That was the question that he asked, but I cannot because I didn't say what was the constant.
So you don't know.
No, there exists some explicit constant. It's in the paper. You can find it. Huh?
You don't know, but you can.
I can't say right now, but it's you can look in there and it's.
He asked about constant and he asked about measures for which there is equality maybe or
For which you have equality.
is there an extreme measure?
I would say that if you could take so suppose you take the matrix A. And you just look at probably the probability measure on the K translates of A. Like something like what Dima was saying. But rather than just take K, you take a K orbit, not of the identity, but of A. Yes? So then I think the two numbers should be clearly the same. Yeah.
And is the assumption of K invariance crucial?
Yes.
So otherwise,
There's a counterexample in our paper, some simple counterexample. K invariance is essential.
and is what the K is exactly the orthogonal group, or
Here's the orthogonal group here.
yeah, in your example. But I mean, how to say? So this is of course not the only subgroup in G. So I mean, is there some special feature of this group, or example, or there is some there is
If you have, huh?
so it is all of n special in this sense.
Yeah, I think it's kind of special. You will see in a moment. Yeah.
Maybe there is a general case when the mu generates a subgroup that sits inside GLNR and then maybe.
Yeah, you can maybe do better, but yeah. Then maybe, yeah.
Another stupid question: is the inequality okay? So the left-hand side, is it obvious that it's less than infinity?
Is the left-hand side less than infinity? That may have been, that may be a consequence of star, but I don't know. But if it's infinity, that's okay.
Of course, but less.
Yeah, then it's less interesting, right? Yeah.
The response always less than log of the norm. So
Yeah.
that's not it's fine.
Yeah. Right.
Thanks.
Yes. Okay. Questions?
I don't have any questions. I just wanted to say that to Evgeny is that K is maximal compact subgroup. All such subgroups are conjugate, as you probably know. So that's the role it plays. Probably it plays a role in the proof.
Yes, yeah.
A lot is known about relative representation theory of G and K.
Yeah.
Happens the representation of G and restricted to K opposed to R2.
Right. So yeah. So that's the theorem. Now I have to say some things about the proof. Yeah. Is this what you were asking? Like, what's special about the maximum compact subgroup?
No, I was asking that play a role in this complete state. So I mean, it is important. All those properties.
Yeah. I mean, all of those properties, including some properties of spherical functions that get involved here. And this is kind of something from outside of dynamical systems, which gets used to prove this result. Okay, so I should explain that. So the analogous statement for GLNC, and UN was proved by Dedew and Shub. And yes, and Shub is okay. No, I should say this theorem was conjectured. This result was conjecture. So this was conjectured by Burns, Hugh, Shub, and Wilkinson in 1999. So it's some conjecture of theirs. And found an analogous statement for GLNC and UN was proved by Dedew and Shub. And is this 2003? Okay, and yeah, so but this turns out to be harder, or turned out to be harder, and the reason is because well, okay, now looking at the proof, the reason is that spherical functions for this pair are simpler than spherical functions for GLNR mod ON. The spherical functions for this pair are just Schur functions. But here there's a zonal spherical functions and they're a bit more complicated.
How do you define the numbers R and L in the complex case?
Oh, how do you define? First of all, R is the same.
The capital R.
Huh?
The capital R.
Well, little r's are the same, they're Lyapunov exponents.
It's maximum.
Yeah, the same maximum. You're taking absolute values everywhere. All along, they're just real numbers. Yeah, it doesn't matter if your matrix is complex. Anybody's going to take absolute value of the eigenvalue. Yeah. So
Was conjecture refers to these. Was conjecture refers to the statement above or the statement below? The statement below.
this theorem.
Oh, this.
Yeah, the real case is what's kind of was important and was conjectured. The complex state, the analogous complex statement is a bit easier to prove, and that was proved here.
There is the complex version of the oscillating theorem as well.
Yeah, oscillated theorem is quite general. Yeah.
Should tell us who is CSS are.
Yes. Armentato, Chinta, Shub,
Thanks.
and me. Okay. I should spell out the names. That's the result. So, okay. So maybe I'll explain a little bit about. Okay, so maybe I'll just say how I got involved in this. So I do spherical functions. I don't do dynamical systems. And so Michael Shub, who's kind of involved in everything, is a colleague of Gautam Chinta at the City University of New York. And so I think Shub asked Chinta this question, and said, "Oh, it's very interesting," and it becomes some question about representation theory. And then at some point he calls me and says, "I have this question in representation theory that would imply something for dynamical systems, and I can't quite figure it out." So then because he had translated, so it's problem. I mean, to actually for somebody to do a problem like this, someone has to actually make the connection. And so this is entirely Gautam that he saw that this problem could be tackled by using representation theory. And maybe we'll say, so Gautam is not the first time Gautam asked me a question, so he asked me some other question, and I solved this question after about 15 years. So he said, "Okay, I'll ask another question." And this question, fortunately, knew how to solve right away, more or less. And so that's how this work was done. Yeah, Oman was, maybe I can't know what is the other question I'm talking about. And maybe even Eyal knows it. It has to do with these multiple Dirichlet series.
You didn't say what's Armentato's.
Oh, right. So I think so. Okay. So Armentato is a student of Shub. They were working on this problem. They had taken this problem and transformed it to a certain integral. So this happened before I came in, so I don't know. This is my conjecture. I mean, the problem came to me like sort of silly fun.
He's a dynamical system person.
Yes, he's a dynamical person. Yes. Yes, exactly. And yeah. Okay, okay, yeah. All right, so I explain. So I mean, now there's two things to do. So first, there's a way of taking this to transform it into a problem in representation theory, and then a solution of this problem. Okay, so how much time do I have? Half an hour. Okay, so I will try to say a little bit about both. So there are some things. So if you have an orthogonal value to measure, actually, let me see. Okay, so okay, so here's the point. So if yeah, let's say so. So let G and K be the Grassmannian of K planes. In Rn. Okay, and if okay, so for G in Gn in G, okay, so maybe I write it like this so that it's the Grassmannian rather than not confuse it with any group. So for G in G, I can define. So okay, so and X in the Grassmannian, I can define that sub X of G. So as follows. So let okay. So yeah. So okay. So this from G this and X in here. So G is a map from the space X to Y, where Y is again equals GX is also it's a K-plane, right? But the point is that both of these have, since we're in Rn, we have canonical volume forms. So we can define. So let's take some. Take some. You take a volume form here, and you take some volume form here. Yeah. Okay. So okay. So what I'm saying is that let's say the kth exterior power of G gives me a map from wedge kx to wedge ky, and these have preferred bases. So because of the orthogonal structure, so det x G is this has so here I can take omega x and omega y, and wedge kg of omega x is det xg of omega y. So it's how this restriction distorts the volume. Is this clear, Dima? Okay, there's probably a simpler way to say this, but you have an ambient, you have an ambient Euclidean structure.
I'm not sure. What is this omega x?
So you choose, so okay, this is a one-dimensional space, but it has a distinguished basis vector.
Yeah, what was that?
Okay, maybe. Yeah. So I just choose orthonormal vectors, any collection of orthonormal vectors, and I take their wedge. This is unique up to some sign, right? And I do the same thing in the other space, and then I can define this determinant. Yeah, well, I actually just care about the absolute value. So, okay. I don't know if one can do something with the orientation, but the absolute value is well defined. Dima, is this clear? Okay. So what is the issue? So okay, so some main theorem, which is I think at least due to. So I don't know. It's ambiguous, for instance, but they say that it's well known or older or something. I don't know. But what they explain is that this sum R equals 1 to k of Ri that we care about. Well, we care about max of this and 0, but this sum can be written as a double integral. G in G, X in the Grassmannian, X in the Grassmannian of log of the absolute value of determinant X of G, and then you average over the Grassmannian, and you do a mu integral. Okay, so this is somehow not so difficult to write these. Yeah, to okay, this is. It has a measure.
Probably.
Huh?
Different.
Yeah, okay. So first of all, there is a natural measure on the Grassmannian, which is the quotient of the Riemannian measures on the Kn mod k sub n minus k cross k sub k. Yeah, some Riemannian measure. So you have some, once you have a Riemannian manifold, there is some compact Riemannian manifold, there's a Riemannian measure on it. Yeah,
So this measure does not depend on mu, so you just fix one measure on the Grassmannian.
First of all, it's a homogeneous space, so this measure is invariant. So it's unique up to normalization invariant measure on the Grassmannian. You could just normalize it to be one, or you could say it's actually coming from the Riemannian structure, in which you get some regulated by some interesting constant, which is the volume of the Grassmannian. And it's the quotient of the Riemannian volumes of the groups, which is actually very interesting. Just if you have a compact group, then there is the Haar measure, which is just normalized to be one. But on the other hand, you also have a Riemannian measure. So you can ask what is the volume of the group with respect to the Riemannian measure. So this is an interesting, very interesting formula, and McDonald wrote a paper on this. So the volume of a compact group, and it's great. Anyway, it's very, very interesting, very nice paper. If you haven't seen it, you should look at this. It's quite good. Anyway, so for here, okay, this is some statement, and if it's okay to have this be true up to constant, then I don't have to, I just say that I take the invariant measure on the Grassmannian. Grassmannian is a symmetric space. It has some, for a compact group, so it has some measure.
Is it kind of black box, or there is some reason why they should be true? So, I mean,
it's a sort of a black box. I mean, I wasn't prepared to say anything about this, but it's according to what Shub said, well, this is standard. But maybe it's only standard because you thought about this.
There's something similar in the paper of Fürstenberg.
It's standard, right?
Paper of Fürstenberg, he has a criterion for when there is a positive Lyapunov exponent.
Yeah.
He expresses the Lyapunov exponent, the top one, not the sum.
Not the sum, yeah.
It's an integral of a projected space.
Over projected space. Okay, very good. So this is some extension of that.
The exterior product to get the sum of the top Lyapunov exponents, I think is due to Raghunathan.
It's due to Raghunathan.
Yeah, Raghunathan.
Raghunathan. Okay. So then this maybe, maybe this is due to Raghunathan, this idea. Okay. So it's some classic idea. Goes back quite far. Okay. Yes. All right. So you can see how ignorant I am. So you were telling me this in yeah. Okay. So yeah, maybe Raghunathan. Right. So this right. All right. So this is some integral over the Grassmannian, and we want to do some integral over the group of we want to bind this expression by so there's some technicalities. I want to do a plus here and I want to do a plus here, and then I basically want to bind it by so I want to bind this integral by something like this. And so I want to have some inequality of this sort in order to prove my result. Okay, so this is the first idea, or idea A. Okay, so idea B. How do I relate this boxed integral to that quantity? So idea B is this picture. So I take, on the one hand, I take the group K, which is O and R. And then I take, let me call this Grassmannian. I call this Grassmannian Y. Okay, so K is O and R, and Y is this Grassmannian and K. And let's say G is in something G, so some element of GLNR, and I will look at sort of an incidence variety, VG, where VG and VG consists of pairs K and Y, such that KG of Y is equal to Y. So Y is some K-plane, oh, too many Ks, but never mind. Y is some hyperplane, and G is some element, and G is not Y to Y, but I look for those Ks such that K times G maps Y to Y. Okay. Okay, and now I have two projections. I can project onto the first factor, and I can project onto the second factor. And yeah, so yeah, this okay. So what I'm trying to estimate is some integral over here, and I actually want to relate it to an integral over there. But here it's going to be an integral involving this measure mu, and if the measure is K invariant, then I can compute this integral. This is the idea. So, all right, so maybe I can say what the theorem is in some generality, and then you apply that theorem to some appropriate function. So, yeah, this theorem isn't sort of explicitly stated in our paper, but I think it should have been, because it might be useful in other contexts. We prove this theorem and use it for one specific function, but it's a nice theorem.
For you raise, so about this statement A.
Yeah.
So there's some special interesting case where A is N. K is N. So in this case, the Grassmannian just 1 point. And
Yes.
the claim says, the theorem says that the sum of all exponents is the integral of the logarithm of the determinant of the matrix.
Yeah.
Is there some clear explanation or some hint why it should be true?
Yes,
So, yeah.
because when you look at what happens to the volume, it becomes an additive rather than a sub-additive process. Instead of taking the norm of a product, we have the absolute value of numbers. It becomes additive, and then it becomes a consequence of the large numbers. That's actually very important.
Yeah.
When we take the sum of everyone, it becomes much easier. Because the determinant is a number.
Yeah. Thanks. Yes. So, all right. So if okay, I want to state some theorem, but there's maybe not enough room. Okay, but okay, maybe I can do this. So suppose phi is a function. So this is what VG is, and now suppose. Ooh, I'm running out of time. I'm sort of out of time, more or less, or I have still a little bit of time. I can go for
10 minutes.
Huh?
You can definitely use another
10 minutes, okay.
Yes.
But if it's some hard deadline in 10 minutes, then I should maybe just start using the 10 minutes now. You think, or? Okay.
Doesn't have hard laws.
Very good, yeah. It's
But if anyone has to leave, then please.
okay. As long as it's a weak law, I think. So what I want to say is that suppose I have a function, suppose phi is a function on y. So I have some function on the Grassmannian, like, this function. Then I can define a function on K. Yeah, let's say phi of y is a function on y. So define psi of K to be a function which is the supremum over these pairs ky in VG of phi of y. So I have some function phi here, and I have a point k here. So I look up here, look at all the points sitting above this, look at all the phi values here, and I take their supremum. Of this set. Yes. Okay, the key result, maybe I write it here. Key lemma. No, okay, maybe I write it there because I want to say more about this. So the key result from which what we want follows.
I want to get
Are these maps surjective?
I want.
I1. Yeah, I think so. Yeah.
So psi is everywhere fine, yes?
Yeah, at least almost everywhere. I don't know, but I'm going to make a statement which involves integration. And so the statement will be correct. So the key lemma is that the integral of k psi k dk is greater than the integral of phi dy for some there exists constant c. The lemma, there exists constant c such that for all phi, maybe I call this sci-fi.
That C depends on G.
Yeah, G, yeah, everything constants depend on G, just not fixed at G. So basically C depends on N. I mean, they're all different constants. G depends on N.
On the stones,
No.
it does not depend. I mean, the construction doesn't depend.
Oh, does C depend on small g? That's a good question. I think not. No, that's the whole point. That it doesn't depend on G. Does not depend on little g. Yes, yeah. Right.
But the function does depend, yes? I mean,
The function.
the function psi. So given a phi,
No, it's phi. Yeah.
find psi does depend.
Yes.
But the constant does not, right?
The constant does not. The constant does not. Yep. That's right. So, okay. So how is this lemma proved? Or like, what can one show? So this is, okay. So, I mean, there's a sort of a chain of variables to try to take the integral from here to there. And what shows up is a certain Jacobian in this, right? So, so proof sketch. In this, so what is true is that, where is this, does this Jacobian show up? Yeah, so what actually shows up, and I'm getting a little bit, Um, okay, so it's a little. So you do a change of variables in the integral, in the integration. And a certain Jacobian shows up. Which depends on G. Shows up. So J of G. It occurs. And the thing we want to prove is that this J of G, main point, we need to show that J of G is greater than or equal to 1. Okay, so I'm not explaining enough details so that you can understand this, but that's what happens. Okay, if you just follow if you just do the calculus, then you will see that if you knew that this Jacobian was, what is this Jacobian? So what is this Jacobian? So JG it's actually a determinant. So if I write G as K times so KG, yeah. So KG maps this KG maps Y to Y. So if I write KG as some B1, B2, 0 star, where this corresponds to Y and this corresponds to Y per, right? KG is mapping, it's mapping Y to Y, so it's in this parabolic form. Then JG is determinant of 1 minus K1 B1 tensor K2 B2 inverse transpose averaged over OK and ON minus K DK1 DK2. So finally, we have to prove.
The two keys that appeared,
This is like so bad.
they were separated before, but
Now suddenly it's terrible. Yeah. So yeah, I don't know. I don't know what to say. This is K. This is, I mean, yeah. This is some element of K, and this is the number. I apologize. Okay, so we need to know that this integral is positive. So the first point is that one can expand this integral. One can expand this guy, this determinant. Actually, yeah, so this was the problem that, this is Gautam's formulation. And what I'm about to explain comes in a moment. So the point is, we can write this, we can write this determinant of 1 minus, I don't know, B1 tensor B2 transpose inverse. As a sum over characters of GLN. So this B1 is an element of GLK. This is an element of GLN minus K. And I look at K times N minus K. And I look at all partitions which fit inside this box. So then this lambda gives me a representation of GLK, and the transpose gives me a representation of GLN minus K. So this determinant is the character. So it's chi lambda B1. It's a sum. Actually, I look at something slightly more general. I put a minus U here. You will see in a moment. So I just I look at this. So this series is summation over all lambda sitting inside this. So let's call this box B. So all lambda contained in B of minus U to the J and the Schur function S lambda of B1 times S lambda prime of B2. Maybe minus transpose. Yeah. Okay. Maybe I replace B2 by. Well, yeah. Let me just work with B2, because later on it has to be for only B1, B2. So why wouldn't I just replace B2 transpose by B2 here? So this is the setup. Well, this is the transpose partition. And so what we're computing, capital B is this K by N minus K box. So any partition which fits inside here. No, what is J? This is the size of lambda.
Yes.
Yeah, question?
You just answered.
Okay. Yeah, thanks. Yeah, so it's this guy. And now, okay, so now, all right, so then what we're our JG, or maybe I call this JGU, B1, B2, U. JG involved this B1, B2. So JB1, B2, U is then just the integral. Okay, let me take this empty partition outside. So it's 1 plus summation of minus U to the lambda. Well, okay, lambda is not equal to 0. But then I just do an integral over K1 S lambda K1 B1 BK1 times S lambda prime K2 B2 DK2. Yeah, and doing a K1 K2 integral here. That's what this is K1 K2. Okay, so now what is this integral? So this integral S lambda K1 B1 BK1 is so if so very often it's 0. So this is 0 unless lambda 1 is totally even, unless all parts of lambda are even. Because you're computing a spherical vector inside some representation or spherical function, Cartan-Helgason theorem tells me when there is such a non-zero vector, and so this means that this will just vanish. And otherwise, this is equal to the spherical function. So, okay, so this is the part that's coming from the outside. So this is the spherical function. What's the notation for the spherical function? Usually I write phi sub mu, but I've already used phi for something. So maybe I'll call it C sub mu of B1, where this is the spherical function. It's a polynomial spherical function on G1 mod K1. Okay, so first of all, we wanted to prove that this is bigger than 1. So one good thing is that since this will be 0 unless all parts of lambda are even. So in particular, this sign goes away. The terms of the minus sign just actually drop out. So, so this integral okay, and we one factor that JB1 B2 of 1 is greater than equal to 1. So anyway, in this integral, all the negative terms went away. So let's call this star. So in star, yeah, now I can just finish. So in star, all the negative things went away. So in star, all the negatives, all sort of the lambda odd terms vanish. And then there is a theorem which is proved by Friedrich Knopp and myself that this the spherical function it was C. This is the zonal. Okay, let's call it Z. So this is the zonal spherical function. This has a name. The zonal spherical function Z of B1 is a Jack polynomial. J mu of alpha, where in the singular values, in say, I don't know, A1 through AK, where these are the singular values. It's, sorry. For alpha is a Jack polynomial at alpha equals 2 in the singular values of B1. And that's one. Okay, so this is the theorem by us is that this Jack polynomial alpha mu A1 to AK has a positive coefficient, has coefficients which are positive polynomials. Polynomials in alpha. So now I just put alpha equals 2 and they are all positive. So put alpha equals 2. So all positive. So what this means is that first the minus terms vanish and the odd terms vanish here, which could produce the minus sign, and the positive terms are all positive. So we proved the estimate and we win. That's
Questions, please.
Questions?
Could you please repeat the punchline again?
So first, if I want to prove that this determinant is bigger than 1, right? If I write on the determinant, I see pluses and minuses. So the minuses happen when this lambda is the size of lambda, when it's the partition of some odd integer. But we have a strong vanishing theorem for these integrals. That unless all parts of lambda, even this integral just vanishes. So what survives here after integration is precisely the sum over 7 partitions contained in this box. But then I need to know something about the positivity of this Z1. But for this, Friedrich and I have a formula for zonal polynomials, for Jack polynomials, and there it's positive. So in particular, it implies that these things are positive.
So you use that case ON first for it to be compact so that you can integrate and do correct thing. Second, you probably use that it's Gilfan subgroup, so that's
I mean, really, it's just there's Jack polynomials or zonal polynomials are exactly for this pair G mod K. G mod N.
yes, and then you use that you know this particular a lot about this.
Right.
What about other classical subgroups?
So we need something. We need some analog of this theorem. Is this known for other groups? What is the story here? One could try to extend this.
I know it's just in the theorem.
Yeah.
For GLN.
For GLN. Okay. Yeah, so there are many components, and thanks. First of all, thanks for letting me give this talk because I kind of understood the process of explaining. I understood more, and but
You understood that the measure generates the entire thing. Can't you always embed in GLNR?
but I don't know if this gives an optimal result. Maybe you're right. Huh? In terms of the, actually, I don't know. You can always have but you, how many Lyapunov experiments do you? I mean, if you're actually inside some smaller group, I am not sure what happens for some, let's say, for the symplectic group. I think you can take G mod K, right? And actually, I don't know. I am not 100% sure. Okay, we can talk. I'm here for a few more days, and I'd be very happy to discuss with you. Yeah, and maybe we can figure.
Just in the theorem, the idea was to get the other bound. Because his theorem, his paper was how to show that Lyapunov exponents are not zero.
How to show it not zero? It's very hard. It's like the hard thing, right?
That's what he wanted to show. So
yeah.
Then you need to bound it from the other.
Yeah.
Oh, it's nice.
Yeah, I mean, I should maybe look at this paper and see why they made this conjecture. They do something with this upper bound. Yeah. Right.
I mean, I know these people that are not at all at representation field.
Yeah, these people are not. None of them. Not concerned and so on. They're not. They're really dynamical systems. And yes, in fact, we're hoping this paper will appear in the Journal of Ergodic Theory and Dynamical Systems. Yeah, so that people in ergodic theory will read it. Huh?
They will know who to send.
They will know who to send it.
You know what? There's you know Uri Bader?
Yes, he was a colleague. Yeah.
He has a paper from a couple of years ago on conditions for simplicity of the spectrum. Different Japanese comments. So I think you will also be very interested.
Yeah. Very- So should we stop recording or you stopped already?
Yes, go, please. Yes.
Yeah.